Hi friends, today we have to discuss about Pourbaix diagram. It has some connection with the thermodynamic stability of water. That was also some kind of Pourbaix diagram for water. Pourbaix diagram is an important diagram in electrochemistry and as well as in corrosion studies. While analyzing the corrosion of a particular metal with respect to various environment, means with varying pH, you have to correlate that pH with variation in the electrode potential of that particular element or various species of that element. This actually we are doing with this Pourbaix diagram. So it is a plot of easy reverse pH, or it can be considered as a stability diagram of various species of a particular element under varying pH. To study Pourbaix diagram, we should be aware about 4 kinds of reactions and 3 zones which are common in Pourbaix diagram. So before proceeding to the diagram, we are going to discuss about 4 kinds of reactions. To draw Pourbaix diagram, we have to consider the species. In order to plot a Pourbaix diagram, you should be able to consider the species O2, H2O, H plus, OH minus, metal, metal ion, metal hydroxide and metal oxides. All these species of a particular metal along with O2, H2O, H plus, OH minus have to be considered while developing a Pourbaix diagram for that particular metal. The reactions which need our attention, first one is H2O plus CO2 gives H2CO3. This is actually a common reaction in every metal corrosion. When a metal is exposed in air, definitely moisture from the air will deposit on the metallic surface and dissolution of acidic gases like CO2 can happen in the moisture. When they react together, carbonic acid can be formed which dissociate as 2H plus plus CO3 2 minus. This reaction does not involve any metal, so no need to include in Pourbaix diagram, but actually they can influence the pH indirectly as this equation include H plus. Second reaction is reduction of a particular metal ion to the corresponding metal. M, N plus plus, N electron gives M. Reduction of a particular metal ion to the metal. Cu2 plus plus 2 electron gives Cu is an example. Such kind of many reactions you have heard in electrochemistry. When we are applying an Nernst equation for the same, we will get E equal to E0 plus RT by NF Ln, activity of Mn plus oxidized species on the top and reduced species in the bottom, numerator and denominator, since it is plus. Here reaction is potential dependent. When the concentration of Am plus varies, since metal is a solid, we are taking the value as 1. So the varying parameter is Am plus. When the concentration of metal ion, activity of metal ion varies, potential also changes. So reaction is potential dependent. but pH independent. This reaction does not involve any H plus or OH minus in balanced equation, so this reaction does not depend on pH. This is the second kind of reaction. In third kind of reaction is that reduction of metal hydroxides to metal. Here it was metal ions to metal, it is metal hydroxide or oxide to the metal. By writing the Nernst equation, you will get a relation E0 minus 0.095 pH in the final form. Since this reactions involve H plus, it is pH dependent as well as it is potential dependent. So this reaction is potential as well as pH dependent. And last one is M2 plus 2H2O gives MOH dies. This is not a redox reaction. This reaction does not involve any electron change because in left side you have M2 plus, right side also metal is in plus 2 oxidation state. The only difference is that it was in free ionic state in the left side, but it came to the hydroxide form in the right side. So it is not a redox reaction. Since it does not involve any electron change, it is potential independent, but it is pH dependent. pH dependent. For this reaction, equilibrium constant K can be written like this: log K equal to minus 2 pH minus log concentration of M2 plus. So 4 kinds of reactions we have completed, which are pH dependent, that is H2O plus CO2 gives H2CO3, but no need to include in the Pourbaix diagram. Second one is potential and pH dependent. They are reactions like this. These reactions involve electron and H plus in the balanced equation. Third one is potential dependent but pH independent. This reaction does not involve any H plus or OH minus in the balanced equation, but they include electrons. Just like Fe3 plus plus 1 electron gives Fe2 plus, Cu2 plus 2 electron gives Cu. Fourth one, they are potential independent but pH dependent. These kinds of reactions are not redox reactions as like this. It is the change from one oxidation state to the same oxidation state but in different species. Now, 3 kinds of regions which are important in Pourbaix diagram are immunity zone. Immunity zone means there the metal is stable. It does not undergo corrosion, or this metal is able to resist the corrosion, where they are immune to the attack of external agents. Second one is corrosion zone, where the metal is unstable and they undergo corrosion due to the influence of some external factors. Passivation zone, it is also a corroded form, but some kind of oxide or hydroxide layer is formed around the metal ion, which prevent further reaction and protect the metal ion from additional degradation or corrosion. Such protective condition is called passivation. Now we are directly come to Pourbaix diagram for iron. This is the simplest representation for the Pourbaix diagram of iron. It is a plot of pH along the x-axis and electrode potential along the y-axis. Here you can see E0 values along the y-axis and pH along the x-axis. This actually expresses how the stability of the metal is influenced by the pH under various electrochemical conditions. In this diagram, you can see around 8 lines with different slopes. Generally, 3 kinds of lines can be seen. One is horizontal line like this, horizontal line like this. They represent a redox reaction which are independent of pH, Among 4 kinds of reaction, we have included 3 kinds in this diagram, and among that 3, the reactions which are independent of pH can be represented by this horizontal line. Example, line 1. It is an equilibrium between Fe and Fe2 plus. Fe2 plus 2 electron gives Fe. That is the balanced equation which does not involve any H plus ions. So it is independent of pH. Another line is vertical line. First vertical line is number 3. Vertical line represent species which are pH dependent but potential independent. They represent species of the same oxidation number but in different chemical environment. Line number 3 represent equilibrium between Fe3 plus and FeOH thrice. They both are in plus 3 oxidation number, but in acidic condition, that means at lower pH, Fe3 plus is stable. At higher pH, as we move towards the alkaline medium, FeOH thrice will be the stable species. And third one is diagonal lines or lines with a particular slope. These diagonal lines actually represent equilibrium between species of different oxidation number. Example, line number 5. It is an equilibrium between Fe2 plus and FeOH thrice. Fe2 plus and FeOH thrice. These are 3 kinds of lines we can expect in Pourbaix diagram. So we can explain it one by one. Line 1, which represent equilibrium between Fe and Fe2 plus, where equation is Fe2 plus 2 electron gives Fe. That is the equation. Below this potential minus 0.44, Fe is found to be stable, and above the pH of potential of minus 0.44, Fe2 plus will be the highly stable species. So at a potential of minus 0.44, an equilibrium can be established between these 2 species. Line 2 represents the equilibrium between Fe2 plus and Fe3 plus. Fe3 plus 1 electron gives Fe2 plus. This equilibrium can be established at a potential of 0.77 volt. Below this potential, Fe3 plus is the predominant species, and above this potential, Fe3 plus is the predominant species. Below 0.77, Fe2 plus is found to be the species. So from minus 0.44 to plus 0.77, Fe3 plus is the predominant species in highly acidic medium. Line 3 actually represent an equilibrium between species of the same oxidation number Fe3 plus and FeOH thrice. Line 4 is an equilibrium between three species. Actually it is a equilibrium between Fe plus 6 and Fe3 plus. But here Fe3 plus is in free state, here Fe3 plus in hydroxide form. That is the only difference. Lower boundary of FeO4 2 minus. FeO4 2 minus is called Ferrat, where ion is in plus 6 oxidation number. It will cut pH axis at 2.2 volt. You can see this line. Cut pH equal to 0. This is pH equal to 0 at 2.2 volt. Below this potential, Fe3 plus will be the principal species. Below this line, Fe3 plus will be the principal species. With increase in pH, that means when we move towards the right in the graph, Fe3 plus concentration will decrease due to precipitation as FeOH thrice. When we move towards the right, FeO4 2 minus will get converted to FeOH thrice. Then FeO3 plus concentration decreases. At pH equal to 14, potential is 0.77. At pH equal to 14 means this line. In this line, the line for FeO4 2 minus reach this point, that is at 0.77 or 0.7 volt. Region 1. In this region, FeO4 2 minus is found to be the most stable species. Now consider another reaction. FeOH thrice plus 3H plus 1 electron gives Fe2 plus. FeOH thrice Fe2 plus equilibrium. This is also dependable on potential and pH. So you will get a line like this. This FeOH thrice get reduced to Fe2 plus under normal condition, but above pH 7. That means in alkaline medium, FeOH thrice get converted to FeOH twice. These two reactions can be seen here. FeOH thrice will reduce to Fe2 plus in acidic region, but when we move towards the alkaline region or pH above 7, FeOH thrice reduced to FeOH twice. It is plus 2, this is also plus 2. So plus 3 oxidation number will reduce to Fe2 plus in acidic medium, FeOH twice in alkaline medium. And you can see an equilibrium in this line also. Here you can see the equilibrium between Fe2 plus and FeOH twice. They are in same oxidation number. So they are independent of pH. So various kinds of equilibriums we can see in this diagram. As far as concerned with FeO4 2 minus, in strongly alkaline medium it is the stablest species. In this diagram you can see the stability region of water also, which is shown in green lines. Fe is the highly stable species at low potential under normal condition, but in presence of water, Fe will not be stable. Fe can reduce water to hydrogen, especially in a highly acidic medium. In the same way, FeO4 2 minus is stable in this region, but in presence of water, it can oxidize water to oxygen and FeO4 2 minus get reduced to FeOH thrice. So FeO4 2 minus is stable only in this region. What is the peculiarity of this region? This region. Here you can see a merging of this line with stability region of water. In this region, water is stable, So even if FeO4 2 minus come in contact with water, there will be no reaction and FeO4 2 minus seems to be stable. So stability of FeO4 2 minus is actually possible only at extremely high pH or alkaline medium in a small region. And in this diagram you can see three different zones as indicated in the initial stages of this discussion. Three regions are, one is immunity zone. This is immunity zone. In this immunity zone, iron is protected as iron. Iron never goes to its ionic form. So this is called immunity zone. Above this potential of minus 0.44, it will changes to Fe2 plus. It is a corrosion zone. When potential increases, it changes to Fe3 plus. Again, it is a corrosion zone. But in this region, these ions get converted to hydroxide form or oxide form. Due to this protective layer of oxide or hydroxide, further corrosion can be prevented. So iron is protected due to this layer of hydroxide. So these regions are called passivation zone. So while writing about passivation zone, when you are discussing about Pourbaix diagram, these three regions need to be mentioned there. Immunity zone, where metal is found to be stable. Corrosion zone, where metal continuously undergo corrosion. And in passivation zone, there is a chances of corrosion, but due to the presence of protective layer of oxide or hydroxide, metal is protected. This is only one diagram for iron, but you can do it for manganese, nickel, copper and any metal. So you have to practice that metals also. Thank you.